Part 1. Motivation. Welcome to this lab, where we'll learn how to design control systems for inverted pendulums. Firstly, let's start with a few motivating examples of what an inverted pendulum is and how it can be both fun and useful. Let's start with the fun examples. This is what an inverted pendulum looks like. It is a pendulum where the center of mass of the rod is above its pivot point. Here we managed to keep the rod upright by moving the cart left and right. There are other ways to exercise the torques to control the position of the rod. Here is what is known as a reaction wheel system, which is used heavily in spacecraft. Here we see how the control system manages to stabilize the pendulum in presence of an additional constant torque. We see that it has to pitch slightly to the side to counter the weight we have hung. This is a more impressive demo where the rod is mounted on top of a quadcopter. Quite impressive. This is an exoskeleton. This is another instance of the inverted pendulum. An exoskeleton has active control components that can help people stay upright and walk. You may have heard of or seen a Segway. Actually, a Segway is a trademark, but it has come to refer to two-wheeled self-balancing vehicles like this. Segways are again essentially inverted pendulums. Lastly, rockets are also inverted pendulums. Typical control tasks involve launching and landing. In either case, we want to control the rocket in a way that it stays upright. Here we see the Blue Origin New Shepard in its NS-11 mission, which delivered a large payload on behalf of schools, universities, government agencies and private companies. The thing is that inverted pendulums are actually naturally unstable systems and can be hard to control. Here we see a fellow engineer trying to control a little rocket where the thrust is generated by a fan inside the body of the vehicle. And as you can see, it is quite challenging. In this lab, we will gain an understanding of the dynamics of an inverted pendulum. We will use Python to linearize the system dynamics, design a PID controller, and perform simulations. To do so, we will use a computer algebra system, also known as a symbolic computation framework. We will use this to determine the impulse, step, and frequency responses of the system. We will then determine the transfer function of the linearized dynamics of the inverted pendulum, and this will allow us to design a PID controller. In this lab, we will be using Google Colab, which is an online Python notebook. Alternatively, if you are experienced with Python, feel free to use your favorite IDE or a local Jupyter notebook. Part 2. Symbolic computations. We will be using sympy, which is a package for symbolic computations in Python. You can import it like this. Using sympy, we can define symbolic expressions like this one. Later, we'll be able to use sympy to determine derivatives, integrals, partial fractions expansions, Laplace transforms, inverse Laplace transforms, and a lot more. But first, we'll look at how we can define such symbolic expressions. We start by defining the symbols like this. Having defined the symbols a and x, we define the symbolic expression f. Note here that the sign function we use is a symbolic sign function from sympy. It is often useful to explain to sympy what sort of symbols we have. For example, here we are specifying that x is a real variable and a is positive. This can be very useful to sympy when performing algebraic manipulations. The first thing we may want to do with a symbolic expression is to substitute a variable. For example, say we want to substitute x equals x0 inside f. We first define x0 to be square root of 2 pi over 2. Note that we use the symbolic sign function, sympy.sign, and the symbolic pi, sympy.pi. We then use the method subs, which we apply to the expression f. We do f.subs. Note also that subs expect a list of substitutions. This is what the square brackets are used for in Python. Each substitution is a tuple. Here the pair x, x0 in parentheses means that x is set to x0. To understand this a little better, take this expression, which depends on two symbols, x and y, both of which in this case are positive. We want to substitute x equals 1 and y equals 0. We call the method subs like this. We provide a list of two substitutions. x, 1 means x is set to 1. y, 0 means y is being set to 0. Next, we can determine the partial derivative of a symbolic expression with respect to a symbol. For example, consider again this function. I'm sure you can do this on paper, but to save time and effort, we can compute the partial derivatives of f using sympy. As you can see, it's really very easy. The partial derivative with respect to x can be determined using the method diff and passing the variable x. It is f.diff of x. We determine the partial derivative with respect to y the same way. You can run this code and check that these are the symbolic expressions computed by sympy. As an application, we can determine the linearization of a function of several variables, two or more variables. By Taylor's approximation theorem, the linearization of a function of two variables is given by this formula, and the main challenge consists in determining these partial derivatives. For example, take this function, f, which is a function of x and y. A is a constant parameter. To linearize f, we need to introduce the symbols x, y, a, and we need to specify that they are positive. Well, they are assumed to be positive in this case. Then we define the expression f. We determine the partial derivatives of f with respect to x and with respect to y. We determine the value of f and the values of the partial derivatives at the point where x is equal to 1 and y is equal to 1. We do this using subs. I will leave it to you now to run this code and confirm that this is the linearization of f at the point 1, 1. So pause the video for a few minutes and make sure you're getting the same result. Another thing we can do with sympy is that we can simplify lengthy and complicated expressions. Suppose we have this symbolic expression over here. Then the method simplify reduces this to just sine of x plus y. There is a lot more we can do with sympy. For example, we can generate LaTeX code for our symbolic expressions, and we can copy and paste these in our reports. We can perform simple algebraic manipulations such as expanding, collecting terms, and factoring polynomials. We can determine partial fractions expansions, which is great, given how much time it would normally take to do this on paper. We can determine Laplace transforms and inverse Laplace transforms. We can solve linear systems. We can determine integrals and antiderivatives. So all these make SymPy a very useful tool. Part 3. Modeling and linearization. Before we can design a control system for an inverted pendulum, we need to understand the dynamics of the system. The equations that govern the motion of the inverted pendulum come from Newton's laws of motion. You can find the detailed derivation in a separate video lecture, as well as in my control systems textbook. To get started, suppose we have a rod mounted on top of a car, as shown in this figure. The center of mass of the rod is at the geometric center. The angle between the rod and the y-axis is denoted by theta, and we use the convention that clockwise rotations are positive. So here we see a positive theta. The horizontal position of the pivot point A is denoted by x. This system has 4 state variables. These are x1, which is the horizontal position of point A in meters, x2, which is the horizontal linear velocity of the car in meters per second, x3, which is the angle in radians, and x4, which is the angular velocity of the rod in radians per second. The manipulated input is a horizontal force F, which is exercised on the car. The objective is to stabilize the system at x3 equilibrium equals 0. This is the upright position. At equilibrium, the angular velocity will be 0, and the force acting on the car has to be 0 as well. The system dynamics is described by 4 equations, one for each state. x1 dot is x2, x2 dot is a function phi of f, x3 and x4, more on this later, x3 dot is x4, and x4 dot is another function psi of f, x3 and x4. Functions phi and psi are not just nonlinear, but they're also given by these lengthy and complicated expressions. Here, little m denotes the mass of the rod, big M is the mass of the car, L is the half-length of the rod, and G is the gravitational acceleration. I'm sure you can determine the partial derivatives of psi with respect to f, x3 and x4 on paper, but it's a tedious task to do. Instead, we'll give it to SymPy. So this is what we need to do. We'll linearize psi at the point f(x3, x4) equals 0, 0, 0. The linearization will look like this. To put it simply, psi will be locally approximately equal to a constant times f plus a constant times x3 plus a constant times x4. These constants are to be determined. And well, these constants are precisely the partial derivatives of psi at 0, 0, 0 with respect to f, x3 and x4 respectively. So over to you. Here's what you need to do. First, go to your Python code, import SymPy, and define all the necessary symbols. These will be big M, little m, G, x3, x4, so on and so forth. Secondly, define the expression psi symbolically. Confirm that psi at 0, 0, 0 is indeed equal to 0. To do this, you'll need to use the method subs. To confirm that psi at 0 is indeed 0 is to confirm that this point is an equilibrium point. Next, I want you to determine the partial derivatives of psi with respect to f, x3 and x4. To do this, you have to use diff as we discussed before. Next, you need to determine the values of these derivatives of these partial derivatives at 0, 0, 0. So you take the partial derivatives from step 4 and you use subs to determine their values at this point. And lastly, you need to answer the question, what is the linearization of psi at 0, 0, 0? So pause the video for a few minutes to determine the linearization of psi. So welcome back. You must have found these values for the partial derivatives of psi at 0. And the linearization of psi has this form. We can call this constant c and this constant d. Both c and d are positive constants. We can then say that psi is approximately equal to minus c times f plus d times x3, and this is valid close to the equilibrium point 0, 0, 0. Right, so we have linearized psi. We haven't yet linearized phi, but we can do this later. We have this pair of differential equations, x3 dot is x4, x4 dot is dx4 minus cf. What I would like you to do now is to pause the video for a few minutes and determine the transfer function of the system with input f of s and output x3 of s. This is the transfer function that captures the dependence of the angle x3 on the force F. To do this, you need to assume zero initial conditions and apply the Laplace transform to both sides of both equations. Recall that the Laplace of x dot is equal to s times x of s, having assumed zero initial conditions. So pause the video for a few moments and try to determine the transfer function. Welcome back. So here is how we can determine the transfer function from f to x3. By applying the Laplace transform to the first equation, we obtain s times x3 of s is equal to x4 of s. The notation big X3 of s refers to the Laplace transform of the time domain function little x3 of t. By applying the Laplace transform to the second equation, we have sx4 of s is equal to dx4 of s minus c times f of s. We have therefore obtained two algebraic equations that involve x3 and f, but also they involve x4. It's not difficult to get rid of x4. We need to substitute x4 from the first equation into the second equation and rearrange to obtain this transfer function. The transfer function g theta, that's how we call it, is given by minus c over s squared minus d. Here d, recall, is a positive constant that we defined earlier. I'll leave it to you at this point to determine the poles of g theta and tell whether the system with input f and output x3 is stable in the Bibo sense. Next, following the same procedure, you can linearize phi and determine the transfer function of the system with input f and output x1. Part 4. Open loop simulations. To gain a better understanding of the dynamics of the inverted pendulum, here we will use sympy to determine its impulse, step and frequency responses. At this stage, we don't assume the presence of a controller. The main idea is that given an input f of t in the time domain, we can determine f of s in the s domain. The output will be x3 of s is equal to g theta of s times f of s. The output will be equal to the transfer function times the input. And the output in the time domain will be x3 of t is equal to the inverse Laplace transform of x3 of s. And the inverse Laplace transform can be determined symbolically using sympy. Now, for what follows, you need to know what the impulse, step, and frequency responses of a system are, what these terms mean. You also need to know the Laplace transforms of some basic time domain functions. If you're not familiar with these concepts, it would be good for you to pause the video at this point and do a very quick brush up. Let's start with the impulse response. Simply put, the impulse response of a system is the angle x3 after we kick the car. That is, the input force F here is assumed to be a kick. The impulse response of the system is the output when the input is a Dirac pulse. The Laplace transform of the Dirac pulse is 1. We write F equals 1. As we discussed before, to determine the output, we just multiply the input by the transfer function. We do x3 equals g theta times f. This gives the output of the system in the s domain. To go back to the time domain, we apply the inverse Laplace transform. And this is a one-liner using sympy. Take a moment to run this code and confirm that you're getting the same result. Note that the result here involves a hyperbolic sine function. The hyperbolic sine function goes to infinity exponentially fast. Here with the minus sign, the angle goes to minus infinity, well, exponentially fast. This is in line with what one would expect. Imagine the road is balanced perfectly upright and we kick the car. The car will start moving to the right and the road will start to rotate counterclockwise. Keep in mind that there are two issues with this result. Firstly, it uses the linearization of psi. Therefore, the result is approximately valid so long as the states and input remain close to zero. That is, not for a very long time after the kick. Nevertheless, the result captures something valuable. The output has the tendency, or rather the output starts to move towards infinity, towards minus infinity. And that's important. That's an important qualitative conclusion. Secondly, no friction or energy dissipation has been accounted for when deriving the system equations. We have assumed that any friction is negligible. Again, this is okay if we want to capture the system dynamics in short term, but not good for long-term predictions. Let us now turn our attention to the step response of the system. We ask, what will happen if we apply a constant force to the car? For example, imagine that the car is on an inclined plane. Then a constant horizontal force will be applied indeed due to gravity. Suppose that the force in the time domain is constant and is equal to 1 Newton. The Laplace transform of 1 is 1 over s. Setting the force to 1 over s, we obtain this response, the step response of the system. As an exercise, you can try to determine the frequency response of the system, that is the angle x3 in the time domain, when the force is a sinusoidal function. Another interesting exercise will be for you to sketch the input and step responses of the system for different values of C and D, and discuss what would happen if we increased or decreased the values of C and D. This way you can draw qualitative conclusions about the effect of the length of the road, the mass of the road, and the mass of the car on the system behavior. 5. PID controllers. We'll not say much about PID controllers in this video. Instead, you can go through the tutorial at this link. The link is in the description of the video as well. You can also read chapter 10 in my control systems textbook for further details. Here we will just recall the definition of a PID controller. Firstly, the control error is defined as the desired output, or set point, minus the actual output, or the measured output. In the case of the inverted pendulum, we just want the rod to stay upright, so we'll keep the set point to 0. The control error will therefore be minus x3. The control actions determined by the PID controller are given by this equation. Here we can see the P, I, and D parts of the PID. The gains Kp, Ki, and Kd are the parameters to be selected to have a closed loop system which is stable, has zero offset, and exhibits desirable characteristics, say in terms of overshoot, settling time, or stability margins. The transfer function of the PID controller can be obtained by simply applying the Laplace transform to its time domain representation. Take a moment to check that this is the transfer function of the PID controller. Next, we'll use the control module in Python to design a PID controller for our inverted pendulum. Part 6. The control module. Let me start by saying that we will not be using sympy after this point. You can even create a new Python notebook if you like. Before we start, we need to install and import the control module. To install it, use pip install control. If you're running the code in a Python notebook, such as Google Colab, the exclamation mark at the beginning of the line means that this command will be executed in the terminal. If you're running this in your IDE, you need to run this command in your terminal and without the exclamation mark, not in your Python code. It is highly recommended that you don't install your dependencies system-wide. Instead, if you're running this locally, create a virtual environment and install your dependencies within the virtual environment. You will also need to import NumPy and matplotlib. If you're running this on Google Colab, these are pre-installed. Otherwise, you need to install them using pip install as we did for control. We'll do a little warm-up before we move on to the design of a PID controller for the inverted pendulum. We'll see how we can use the control module to simulate dynamical systems given their transfer function. So consider this transfer function. This has nothing to do with the inverted pendulum. It's just an arbitrary transfer function. In Python, we can represent this very easily. We first need to define the object s, and then we write g like this. This is a bit reminiscent of sympy, but neither s nor g have anything to do with sympy. We can now easily determine and plot the impulse response of g. We call control.impulse_response, impulse underscore response. And this returns two things, a NumPy array of times and a NumPy array of output values. We call these t_imp for impulse response and x_imp respectively. We can then use matplotlib to plot the impulse response. And this looks like this. We see that the impulse response goes to 0, and we can conclude that the system is bibostable. Recall that there is a theorem that says that a system is bibostable if and only if its impulse response is absolutely integrable, and this is the case here. Likewise, we can determine the step response of G. Here we use control.step_response, step_response. The step response looks like this, and we see that it goes to 1 as the time goes to infinity. We can do more with the control module. We can determine the response of G to any input without having to determine the Laplace transform of the input. Instead, we provide the input in the time domain directly. Let's see how we can do this. Suppose we have this very peculiar input. First, we need to construct the input signal. This is done like this. We construct an array of, let's say, 1000 time instants between 0 and 2. And to do this, we use numpy.linspace. And we call this array of time instants TS. We then construct an array U with the values of the signal at the time instance of TS. To determine the output upon excitation by the signal U, we use the function control.forced_response, and we provide as input arguments the transfer function G and the array of time instants TS together with the array of signal values U. Control.forcedResponse returns an object which stores the output of the system. We can plot this using matplotlib as we see here. The response of the system is shown here. And now we can go back to our inverted pendulum. We have already determined the transfer function g theta with input f and output x3. And c and d are given by these formulas. C and d are positive constants. Now, suppose that m, the mass of the car, big M, is 0.3 kilos. Little m, the mass of the rod, is 0.1 kilos. L, the half length of the rod, is 35 centimeters. And g is 9.81 meters per squared seconds. Firstly, I want you to start by determining the values of c and d. You should find that c is approximately 6.59 and d is 25 point something. Just be careful here with the units of measurement. Next, you need to determine the response of the system when the input is u of t equals 0.05 times t to the 1.8 times cosine of t. Here is another exercise. Determine the response x3 of t, so that's the angle, when f is a Dirac pulse and when f is a step as well. Then do the same for x1, and it goes without saying that to do this you need to determine the transfer function with input f and output x1. And this is yet another exercise. It says determine the response of x3 and x1. Of course, this must be done using different transfer functions, one for x3, one for x1. So determine the response of x3 and x1 when the force is f of t equals sine of 100t squared, and t is between 0 and 0.2. Part 7. Controller design. This is the part where you'll design a PID controller for an inverted pendulum. Here we have the system we want to control. The input is the force F, and the output is the angle theta. Suppose we measure theta and we compare it with the set point theta SP. This is always equal to 0 as we want the rod to remain upright. This defines the control error E, which in this case is just minus theta. The control error is fed to a controller with transfer function GC, and the controller outputs the control action U. Note that the force F that is applied to the system is perturbed by a disturbance signal D. The job of the controller is to keep the rod upright despite the disturbance acting on the system. In particular, we want to design the controller so that theta goes to 0 following a Dirac pulse or a step change of the disturbance. But first, I want you to pause the video for a moment and simplify the block diagram. Firstly, get rid of theta SP, and secondly, move D to the left. Now, the closed loop system looks like this. The controller needs to be such that the D to theta transfer function from D to theta be bibostable. Equivalently, we want theta to return to 0 when D is a Dirac pulse. But firstly, we need to determine the transfer function from D to theta. We see that G theta and GC are connected via a feedback loop, where G theta is, so to speak, above and GC is below. We will do this by using the function control.feedback from the control module. Let's see how this works. Firstly, we define our PID controller. We define GC. We choose the gains Kp, Kd and Ki, and it's a good idea to start with Ki equals 0, at least at first. Then we construct the transfer function of this closed loop system using control.feedback. This is shown here. By the way, recall that the transfer function from the disturbance to the output is often called the load transfer function. Your task is to choose Kp, Kd and Ki and then plot the impulse response of the load transfer function. And then you can tune your PID controller. You can pause the video at this point and try to tune a PID controller. So this is how my results look like. This is the impulse response of the load transfer function with the PID parameters I chose. I have plotted the angle theta in degrees, and we see that if we kick the car in the positive direction of the x-axis, the rod will tilt to the left by a maximum of about 45 degrees. And it also takes a long time to return to an approximate upright position. Now let's try to increase the proportional gain, Kp, and see what happens. This is a simulation with a higher value of Kp. We see that the peak angle is now around 33 degrees, but the output is oscillatory. If this is undesirable, we can increase Kd. In this simulation now, we have increased Kd, and we have kept Kp the same as in the previous simulation. We have eliminated the oscillations, and the peak angle is a little over 20 degrees. If we keep playing with the parameters, we'll end up with something like this, which in my opinion looks a lot better. The maximum angle is about 6 degrees, and the rod returns to an approximate upright position within 0.3 seconds. It's neither too fast nor too slow. Having done this, we can now solve this exercise. Prove that the transfer function from D to theta, the load transfer function, prove that the load transfer function is stable. And also, prove that the offset upon a step change of D is 0. Part 8. We're not done yet. To complete the controller design exercise, some more work is needed. We have determined the impulse response of the load transfer function, but not the step response. To put it simply, we need to make sure that the system will work on an inclined plane where a constant horizontal force will be acting as a disturbance. Secondly, we should check whether the controlled system is sensitive to misestimated parameters. For example, we took the mass of the car to be 0.3 kilos. What if it is 0.31 kilograms? Will then the closed-loop system behave nicely? We have used the system linearization to design our controller, and we performed simulations using the transfer function of the linearized system. We should apply the controller to the original, non-linear system and see if it still works, if we're still getting good results. Next, we may want to see how the controlled system will behave in presence of noise. And lastly, but not least, we have been focusing exclusively on the angle theta. What about the position x? There is no control system for x. The fact that we designed a control system that keeps the road upright doesn't mean that the car will remain anywhere close to the starting position. It may be possible that x diverges or even goes to infinity while we control theta. This brings us to the end of today's lab. We learned how to use sympy to compute partial derivatives and inverse Laplace transforms. We learned how to use the control module in Python to simulate dynamical systems using their transfer functions and how to design and test PID controllers. I hope you enjoyed it. See you soon!